Greetings, my name is Elizabeth Wade. I teach basic calculus in the mathematics department at Pellissippi State Technical Community College. This is topic 3 on applications of the derivative and segment 3.3 on optimization. If a function is continuous on a closed interval a,b, then the function will have both an absolute maximum and an absolute minimum on the interval. These absolute extrema will be located at either critical points within the interval or the endpoints of the interval. Let's look at an example. Determine the absolute extrema of the function f of x is equal to 2x to the third plus 3x squared minus 12x on the closed interval from -3 to 3. The process in determining absolute extrema involves 4 steps. First, you need to verify that the function is continuous on the closed interval. Well, the function 2x cubed plus 3x squared minus 12x is a polynomial function, and polynomial functions are continuous from -infinity to infinity, or on their domain. So I'll just simply state f of x is a polynomial. The second step is to determine the critical values of the function in the interval -3 to 3. Remember, to find critical values, we look at where the derivative is undefined. And in this case, the derivative would be 2 times 3 is 6x squared. 2 times 3 is 6x minus 12, which is a polynomial function, so it's always defined on the interval from -3 to 3. And then the other way we find critical values, besides where the derivative is undefined, is to set the derivative equal to 0. So setting this equal to 0, let's factor out a 6 to make this simpler to factor. Continue to factor. We can break this up into x plus 2 and x minus 1. And so the derivative would equal to 0, and we have critical values at x equal -2 and at x equal positive 1. Now, we just stated that if absolute extrema occur, they will be located at either the critical points or the endpoints. So what I'm going to do, I'm going to take the original function and I'm going to plug in the critical values. If you take the number -2 and you substitute it into the original function, 2 times -2 cubed plus 3 times -2 squared minus 12 times -2, you obtain 20. In a likewise manner, if you substitute 1 in, you get -7. Now, we also have to test the endpoints. So the endpoints of the interval are -3 and 3. If you substitute -3 into the original function, you obtain 9, and substituting 3 into the original function, you obtain 45. So notice that the largest value, 20, -7, 9, and 45, is obtained at x equal 3. So we would have an absolute maximum at x equal positive 3. And the minimum value is obtained at x equal 1. So we would have an absolute minimum at x equal 1. Let's confirm this by looking at the graph of this function, 2x cubed plus 3x squared minus 12x, on the interval from -3 to 3. So first we enter our function under y equal 2x cubed plus 3x squared minus 12x. I set my window from -3 to 3, since that's the closed interval that we're considering with a scale of 1. And then for my y min, I use -20 and the y max 30, and I chose a scale of 30. And this is what the graph would look like. So notice that this confirms the results that we obtained from negative 3 to 3. We have the highest point, or an absolute maximum, occurring at x equals 3. We can go to trace, type in 3, and press enter, and we get 45. So that supports the results we obtained. And then we have an absolute minimum occurring right here, which is at x equal 1. Enter. 1 with a minimum value of negative 7. So this supports the results that we obtained. So on this interval, this is the absolute maximum and this is the absolute minimum. This point would be called a relative maximum and this point would be called a relative minimum. Well, that's it for this segment. Now you need to practice this concept by working similar problems. Good luck.